Then it's time to move to our last speaker. So we are going to listen to even more insights in coverage, IoT coverage in remote area. And the speaker is Jean Sant'Ana from University of Oulu. Please go ahead.
Oh, okay, there's something. Okay, thank you everybody for hosting this event. My name is Jean Sant'Ana, postdoc from University of Oulu, and I've been giving some first insights in the analysis of coverage of HAPS for IoT in remote areas, of course. That's like the topic of this webinar. So I think if you're here since the beginning of this webinar, you've seen these next two slides. So this is the structure of the Ensure 6G project. This talk is related to this first part, so connectivity in rural areas. And then first question that became like to motivate the user heads of the study on these kind of technologies, like why not to use just to use third-party solutions, for example, Starlink, which is the one that everybody talks about recently. So you've probably seen this picture that Nuru showed. This is a quite old picture, actually, like we took from the beginning of our project, I believe. And then before coming here, I was like, okay, let me check it because you never know, like they are launching satellites all the time. And then, well, if you check it, it's quite similar. And I think, like in the beginning of the webinar, we were discussing a little bit about like why is it like that. So one reason it's most like business, as we discussed. So not that many people in these areas. And also it comes with the like how the constellation was chosen to be. So you can see like this part where there's almost no satellites. Of course, there are a few satellites that pass here. And these satellites that pass through this area, you can see that they have some kind of vertical/diagonal orbit. And that's why they end up passing through this region. But most of the satellites that are in the southern part, let's say, they have this tendency to be more horizontal or diagonal, but towards the center of the globe. So they keep rotating towards the center of it. So you can think about like, what if a country like Finland and Sweden wants to have some coverage, like can they trust completely on a third-party solution on a company that maybe it's not that interest in the commercial, maybe it's only interest in the commercial view of it and not, for example, in serving areas where nobody has connectivity or something like that. So it's always a question to make. So just quick overview, like very simple about HAPS. In this work, we used very simple parameters. We didn't do a very intensive study on the functionality of them. But basically, so they, like with them, we can have some certain control of the area. So on the right side, you can see two types of HAPS. The first one, it's the Zephyr. Now it's from this Auto HAPS, but I believe it was from Airbus before. It was project more than 20 years already. And well, there are some other projects, and nowadays the projects going on, they have this kind of HAPS with the flexible wing, which is the one that you see on the top part. And then, okay, yeah. And then there are these kind of these other types that you can see down. That is the balloon type. This was discontinued by is it by Google and then was bought by X company. But nowadays it's just discontinued. And then like the ones that came after this are these kind of balloons that are like the Zeppelin style of HAPS. But anyways, so the altitudes of them goes from 8 to 50 kilometers. There's altitudes like they kind of depends on the kind of group studying them or the alliances studying them. But You can say it's not as low as a UAV, not as high as a LEO satellite. Another pro of this, because of this altitude, that there is possibility to indoor or communication without line of sight. First, of course, it depends on technology parameters, but we can see that there are some room for that. Well, the cons, it's not a mature technology. There are not that many companies still going there. They are, for now, like limited by the battery weight. So most of them are powered by solar energy. But like there's a limited time where they can keep working there without landing. So we have to wait for battery technology to improve so they can improve the flying time. And because of not being mature technology, it's still hard to say they are a long-term solution. So that's why we are doing research on it. Then just very few brief of the technologies we choose to study here. So the reasons, like we wanted to first do some check of HAPS for IoT. The reason to doing LoRa and LR-FHSS is because we had some previous studies on that. We wanted to like analyze something quick. We had previous work on this, was easy for us. So LoRa and LR-FHSS are both physical layer technologies from LoRaWAN. LoRa is a bit older, was the first they released the chip spreading spectrum modulation. It has 7 spreading factors that basically you exchange the transmission rate to reach longer distance. So with SF7, you transmit faster, but you don't reach that further. The opposite with the 12. And then LoRa, compared to LR-FHSS, has lower power consumption and it can benefit from multiple gateways. There are many studies showing that. So very good for ground networks. And then there's LR-FHSS. It has a frequency hopping spreading spectrum. It's divided into like its transmission packets. It's divided into header and the payload. The thing with this technology is that it has some replication inside the headers. So headers are transmitted 3 times over different very narrow channels. And the payloads, they are coded with convolution code with 1/3 or 2/3 rate. And then this whole coded payload is split into 50 bits fragments and then transmitted over several channels. They are 488 channels, hertz channels. And then for successful transmission, you need 1 header and 1/3 or 2/3 of all these fragments. So you have some redundancy from the header and from the fragments. All of this makes this technology makes it a very high interference mitigation. And also it has a very longer communication distance. You'll see this in the results a bit further. So this makes LR-FHSS very interesting for non-terrestrial communication satellites and HAPS. This was one of the reasons it was designed, and it's being studied and used a lot for these kind of scenarios nowadays.
Do you know the hopping rate?
It's so the header takes 233 milliseconds, and then the payload is 102 milliseconds each.
One hop per second also.
No, actually more, because then for each header it transmits the header and then you hop to another. And then transmits another header hop. So for each 233 or 102, it keeps hopping. And then the number of there's some structure of these hoppings to follow the regulations. So there are many. I think overall you can think about 35 channels to hop. But before this 35, you also choose 1 out of 8 grids to hop. So there's a lot of. That's why it's very good to mitigate interference. So this is the system model we adopt. So very simple. We have free space path loss with rich and fading and log normal shadowing. and the parameters of this model, they are function of the elevation angle. So we can kind of see the elevation angle being like important on this case, of course. Then the coverage area, we set up like a circle where the maximum radius is given by the minimum elevation angle that we consider for coverage. And then also, so we have this model, and then we also have like transmissions might incur into collisions, and if there's a collision, there's also an voltage. So first, for the connectivity results, you probably see some similar pictures in Nuru's presentation before. So the first result, we just set the HAPS at 30 kilometers height, and then we just change the distance of the devices and check the connectivity probability. You can see the distance and the elevation angle axis, like they are basically the same, the equivalent. And then, of course, you can see that the higher SF, we have like a bit higher outage because the distances are a bit like not as long as the higher spreading factors. And you can see the LR-FHSS is the same as the SF12. So we can see that like there's still some good margin, especially for the SF12 and for the LR-FHSS to work with this kind of setting of parameters. But then another interesting result we have is that maybe we are interested in the worst part of the network, which is at the border. So how is the coverage there? So we just set similar results, but then with the minimal angle. So for that, we just kept increasing the HAPS height to get this result. So as you increase the height with fixed angle, you have the radius of the network. So we put the device on the radius of this network. So you can see that of course, for a smaller elevation, for a smaller height, we have like better coverage, but then this incurs into a smaller footprint, so a smaller coverage area. So here you can see a bit of the trade-off of the HAPS height and the elevation and the area coverage. And then finally, it's not like a very novel result, but this is showing the collision probability of the LoRa and LR-FHSS. So this result is like not novel for this work. There are some previous works showing that. But then here we can see that the collision probability for the same number of devices from LR-FHSS, it's way smaller than for the LoRa spread effect for LoRa. Thus showing what we said before, that the scalability of LR-FHSS is way stronger than LoRa. So just some conclusions and further work. So this was a very basic and first insights of HAPS for IoT. We showed that LR-FHSS proves to be a better option than LoRa for the HAPS communication as well as the satellite, and that the HAPS might be a potential future solution for this type of IoT communication. And for future work, we are planning to do some kind of technical economic analysis of HAPS LEO satellites and UAV remote IoT and compare them, investigate these aspects like the reliability and scalability as we've done here, but also costs, energy consumption, the architectures of the HAPS system, and also the regulatory challenges that we might face. And that's it. Thank you.
Good, thank you, Jean. One short question, if there is any.
Do we have this frequency hopping system? We have LoRa, but do we have this frequency hopping so that you can do real measurement-based comparison?
So this has been like quite new compared to the other LoRa. Across Europe, there are many people like already like doing works with that, and there's like real setups, especially for satellite communications and LEO communication. I don't know if we have at the University of Oulu now, but like we can definitely buy the devices and check it.
Yeah, because if it's interesting, it would be worthwhile to have it in test network.
Yes, for sure.
Yeah.
Good. Thanks again, Jean. That brings us to the end of this webinar. So I want to thank again, first of all the speakers for their interesting insights. I think we have learned a lot, got new insights about and perhaps some more about the challenges, about the verticals in remote areas. And even more, I want to thank the audience, all you in the audience, for attending this and for listening and showing interest in the work of these two projects. So with that, I close this webinar and say thank you to you all. Bye-bye.
Thank you. Bye-bye.